Hello. Today's lecture, we will finish the chapter 6.2. We've started about the diodes and we'll go to the applications for the diodes, which are rectifiers. Then we will move to sensors and instrumentation. Then the last of the Watson bridge. For the supplemental problems associated with diodes and rectifiers, our problem is 100 to 107. And the problems, not the problem, associated with Watson bridge, 108 to 110. Now let's remember when we talked about, recall that when we say that the diode is only allowing the current to flow in one direction, which is this direction. And the polarity, this one, the positive, this is the negative. So we have two cases. If VD positive or the voltage polarity is positive, then the diode will have a short circuit and the current will flow this way. And if VD is negative, then it will be an open circuit, so that the current cannot flow in the opposite way. This is basically what's the ideal diode. This is the ideal. So we see it's like switch, turned on, turned off, but it's uncontrolled switch. So why it's switch? Because sometimes it can be on, which is short circuit, sometimes it can be off. That's what the switch do. And why it's uncontrolled? Because I cannot say, let me open it now or let me close it. I don't have any access. The only way that it's being turned on or turned off based on the polarity of the voltage or based on the current direction. So I don't have an access direct to this switch to control it. That's why it's uncontrolled switch. And the word uncontrolled is very important. So one of the applications for using the diodes, and this is very common, which is called half-wave rectifiers, or in general, something we call it rectifiers. The general name, rectifiers. So when we talk about what are the rectifiers, they are one type of power electronics, which is to convert AC to DC. This is the type of rectifiers. So whenever I say rectifier, it's something that converts AC to DC. And there are many applications for that. Last lecture I have mentioned many applications about this. So now I just want to go to the basics, how we are using these rectifiers. So the rectifiers also are divided to groups. One of the groups of rectifiers is called half-wave rectifier. This is type number 1. So half-wave rectifier, in general sense, it is like for any rectifiers converting AC to DC. So half-wave is this circuit. This is the equivalent circuit for half-wave. And we have only voltage source, single diode, and resistor. This one can be the load. It can be the laptop charger. It can be your cell phone, etc. It can be anything that works on DC. So it should support DC. And most likely, since we know we are in AC, Vs of t should be sinusoidal. So the waveform looks like this. Is that right? Then what will happen? So we have the voltage, a positive side, and we have a negative side. So for the positive side, this one, the voltage at capacitor, will be positive at the positive side, and the current is going this way. And for the negative side, this one will be negative. So it will be turned on the positive side and will be turned off at the negative side. Positive cycle or negative cycle. So how can I do this? By saying, like, if Vs of t larger than 0, which is in this positive cycle. This is the positive cycle, this is the positive cycle. So the diode will be, the voltage of the diode will be positive. This means what? This means the diode will be short circuit. That's what we know, it's positive. So the diode will be short circuit. Vs of t larger than 0, it will be short circuit. While if Vs in the negative cycle, the diode should be what? Short circuit. I'm sorry, open circuit. That's what we know from the diode. So this is an application of, by saying we have two equivalent circuits. Since Vs of t has positive and negative cycle, so we have two equivalent circuits. The first equivalent circuit, when it is positive, so when it's positive, the diode will be positive, so it will be short circuit. And when it's negative, the diode will be open circuit. Is that clear? Now, how can we plot the waveforms? How will it be? So, if you want to plot dr of t, so we know if it's short circuit, the current should flow. If there is open circuit, the current will not flow. Is that right? So, if we say that this is Vs of t, if I want to plot the voltage at this resistor, Vr of t. Remember, this one for the positive cycle, this one for the negative cycle. So for the positive cycle, the current is flowing. Is that right? And what's the voltage? Vr of t. What's the value for this circuit? What do you think? The voltage at this resistor, how much will it be?
Same as the source.
The same as the source, exactly. Because they are in parallel, there's no other elements between them. So the same as the voltage of the source. So at the positive cycle, can I divide this? At the positive cycle, it will be the same as the source. Because they are in parallel. Now at the negative cycle, I'm in this equivalent circuit. How much will it be, the voltage?
Zero.
Zero. Right. Because there's no current flowing. So 0. Now here I'm at the positive cycle, which is at this equivalent circuit. So it's how much will it be? Again, the same as the source. Then 0. So if you assume, for example, this one is 10 volts, this one 10 volts, this one minus 10. So here, since this is the same as the voltage source, 10 volts. Now if we want to plot the currents, if we say the resistor equal to ohms, so how can we plot the currents? For this equivalent circuit, the current is flowing, is that right? Because it's completed circle. So how much the current?
V over R is 5.
Right, V over R. So the peak value 10 over 2, which is 5. Is that right? So then it will be the same waveform, but it is different magnitude, which is 5 ampere. Now what's about this? In negative cycle, it's open circuit. What does this mean? What does it mean when we have open circuit? How much the current? 0. Then the same, then 0. Okay? So now we see this equivalent circuit. Do we see any DC value? This is not actually DC. So half-wave rectifier alone is not efficient to be a DC. Even if it's AC to DC converter, here the average value will not be 0. So I can get somehow, but it's not enough to say we have rectifier, or we have converting efficiently from AC to DC. So there's another approach, or there's some modification on this to make it going to rectifier by adding a capacitor in parallel. So why do I add this capacitor? Because I want to make the capacitor charge and discharge. This waveform we see here during the negative cycle, what's happening? It goes to zero direct. While if I add a capacitor, the capacitor will take time to reach zero. So it will discharge during this period instead of going to zero. That's why we are using the capacitor. So we can avoid going this, we call it discontinuous, which means sometimes goes, like with the waveform, sometimes goes to zero, sometimes with the waveform, sometimes with the waveform goes to zero. So we don't need this, or we don't want this, it's undesirable. It's even like affected on the loads. So we add capacitor to be discharged. So how the waveform, or for that, this is the equivalent circuit for it. So if you want to plot or the equivalent circuits, if Vs of t is positive, so what's happening? This is the voltage source. The diode will be short circuit. The capacitor will be charged, and the resistor, the waveform of the resistor, it's positive. Okay. Now for Vs of t is negative, then it will be open circuits. The diode open circuit. Now what do we have? We have the capacitor in parallel with the resistor. So at the negative cycle, I cannot say VR will be zero because I have the capacitor, and the capacitor is being charged before the switching. Do you remember the transients when we said the switching before and after? If you remember, like the transients, we said that this is switch, capacitor and resistor. The same as the transient circuits, but instead of making the switch, we put the diode, so the diode will be open, turned on, and turned off direct. So here, I don't want to go to the waveform, to the equations like differential equations, etc. I just want to focus on the waveform. So here, what's happening? The capacitor being fully charged, then the resistor will be the same as the source voltage. Then after VR of t, what happens? When it goes to zero, the capacitor starts to be discharged. So if the capacitor is big enough, then we will not reach the discontinuous one. Which means, let me draw the waveforms and let's see. So this is VR V as the source. Now VR of t so what's happening, we see this peak value. So VR goes to the peak value. Then the same as the source. At this point, the source starts to be decreasing. But the capacitor will not allow this to be decreased in that fast. It will slow it down. So it will be like this. So you see, it's not slowing down in this slow. The reason again why, because the capacitor is fully being charged. It will not allow this here. Then until this point, we will see which is larger, Vs or this waveform. Until C go to this point, it will goes to charge again. Then the same. So in this waveform, we see it will not touch the zero. So it will still have some positive value. And if the capacitor is big enough, we will not see that large slope. If the capacitor is very large value, then it will be very smooth or with lower slope. Okay? What's about the currents? For the currents, the same waveform as this one, but with different magnitudes, such that if this one is 10 volts, for the voltage, this one is 10 volts. While for the currents, we will say V over R, which is 10 over 2, 5 ampere. Then, if you plot this, the same, and here, 5 ampere. Is that clear how we plot the waveforms? And don't forget to label the axis as time, seconds, 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 and decimals. Is that clear? So this is the other type of rectifier, which is half-wave rectifiers, type number 2. Half-wave with capacitor. So we have half-wave without capacitor, or with regular half-wave rectifier, then half-wave with capacitors. And we found that using the capacitor make a big advantage. Clear? Now, what's about if we modify more? Can we make a better performance? Even adding the capacitor sometimes, I cannot make it like that pure DC. We make something called full wave rectifier. And again, full wave rectifier is still a rectifier which converts from AC to DC. And we are using this to make it easier by using this 4 diodes. So with this 4 diodes, what's happening? We can call this one D1, D2, D3, D4. And our concept is the same, convert AC to DC. So if we have 2 cases for these diodes, if Vs is positive or if Vs is negative. If Vs is positive, the current is flowing here, here, through V1, through VR, and returning through D3 to the source. If Vs is negative, the current is flowing through D4, then to the resistor, through D2, back to the source. Again, if the current, or if the voltage is positive, the current is flowing going out from the positive here. Then it goes to D1, then to the load, then follow this line, then through D3, then back to the source. And if it is in the negative, if Vs is negative, the current is flowing here through D4, then to the load, then to D2, then to the source. Clear? If someone is kind of like miss between those, so we can say this, the following. If Vs of t is positive, then D1 and D3 short circuits, while D2 and D4 open circuits. If you happen to like miss between. And if Vs of t is less than 0, then D2 and or D4 are short circuits, while D1 and D3 open circuits, which is the opposite. And you know that SC, which is short circuit, C open circuit. We mentioned this. Okay, so again, this is the rectifier. If Vs of t larger than 0, then D1 and D2, D3 short circuits. So what's happening here? The current is flowing here, then goes to D1. This D1 is short circuit, and D3 short circuit. The current flowing here. Follow the arrows. Follow the arrows. Flowing here, 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 here. You see the arrows? This is how the current is flowing. Now, if Vs of t is negative, then D2 and D4 are short circuits. So this is D2, this is D4, So the current is flowing here, here, here. Follow the arrows. Just follow the arrows. Okay? Any questions? Now, how the waveform will be? So this is Vs. Now, this is Vr of t. So, basically, the waveforms at the positive cycle, the current is flowing. Then it will be like this. And the negative cycle, the current is flowing but in the opposite direction. So it will be like this. Then, the positive cycle, like this. The negative cycle, like this. So this is the waveform. So it looks like we make the absolute value for the waveform. So if this one, 10 volts, minus 10 volts, these are all 10 volts. Clear? Any questions? So the circuit, equivalent circuit, looks like complicated, but the waveform or the concept of operation like this. What's about the currents? If the, let's assume the resistor equal 2 ohms, then it is V for R is 10 over 2, which is 5 amperes. So the current, the same waveform as the voltage. So those are all 5 ampere. Any questions? Now, what's about adding capacitor? So adding capacitor, this is, we can call it part 4, full wave rectifier with capacitor. The equivalent circuit is the same as the full wave rectifier, but if we add capacitor in parallel with the resistor. So if we add capacitor, how will it be? Let me plot the waveforms again. Sorry about that. I think it's very good. This is VR T, and this is I. So by adding capacitor, here is the peak value, here is the peak value, here is the peak value. So this goes here, then it starts to discharge until this point, then it will be charged, then discharged, charged, discharged, charged, etc. So we see what the waveform is being charged and discharged frequently. It's not like for half-wave rectifiers who was charged and discharged in another positive cycle, while here it can charge in the negative cycle as well. So here it can charge in negative cycle, while for the half-wave cannot do that. And the reason for that, because in the negative cycle they are all positive, so it can charge here, it can charge here, it can charge here. Clear? What's about the currents? the same waveform. And we can put the magnitudes of this one 10 volts, this one minus 10 volts, so here these are 10 volts and this one 5 amperes. So let's look at the waveform for the current here and the waveform for the current here in half wave, full wave, half wave. So we see this waveform is like, we call it the differences between this part and this, between these two, are very small with respect to this. Is that right? This makes the half-wave rectifier better. And if we have a good capacitor, then this one will be smoother and smoother. So we can get the DC. Okay? That's how we get the DC in real applications.
You got a question?
Yes.
So, if you do have a large capacitor, doesn't it require a larger startup time for it to be as effective, or for it to be fully effective, or does it start working immediately?
In general, like for the first cycle or this period, we are not worried about it. We're worried what's happening later. So it might take time during the first cycle, while after that it should be okay. So one also of the other applications for the diodes in something we call it LED. I think we are all familiar with this for the light bulbs, LED light bulbs. So the LED are types of diodes, but why we call this LED? LED stands for lights emitting diodes. That's what does LED do. So LED are type of diodes, which is from power electronics. And how it works, we have two modes of operation, or two ways of operation. If I want to connect multi-LED, I can connect them into series. And the advantage of series, they are sharing the same current. Or I can connect them in parallel. And the advantage, they are sharing the same voltage. So can anybody tell me what's the better performance? Or what's the better connection? To connect them in parallel or in series? Parallel. Why? Can anybody tell me why? Right. So if I'm in series, let me assume that LED number 1 for some reason has misfunction or burned out. So this will affect the link number 2 or the other connections. So the current will not flow. If the current will not flow, all of the diodes are connected in series will be turned off. So this kind of not good approach because they will be turned off. While if we have for this equivalent circuit, if LED number 1, well, there was something wrong with it, the current will not flow here. Okay, that's fine. The current can still flow here and can still flow for the other. So if there's something wrong, that's fine. The circuit can still work. While here the circuit cannot work if one of them was not working. Okay? So we can say if one LED goes out in series circuits, all other LEDs are disconnected. So that's why we prefer connection in series and in parallel. Any questions about rectifiers in general, diodes? So that's what's required from you. Is just to know the waveforms, how to analyze the circuits, how to know the equivalent circuits, and plot the waveforms. And if there is if you want to solve the circuit, just to know the currents if we have such that when I draw here the voltage, and when you plot the current, you need to know how to find the current by saying Ohm's law V over R. This is the only calculation. Otherwise, you need to know how to plot and how the switches are working. This is what required from you. You will not be asked how fast the switching, or we will not go into the transient analysis into this part. So it's just the plotting and what I discussed in this lecture and in the supplemental problem set. This is all what's required from you, because this one is very complicated analysis, and they are taught as another course. So this part of course is called power electronics. That's electrical engineering are taken in, and it is advanced level for grad school and or high undergrad school.
The question right here. Which of those perform better in light output? Do they output the same amount of light, or does one of these perform better than the other?
Yeah, in general, like if they are sharing the same current, they should have the same illumination, the same. While if they are in parallel, depending on their resistor, but also the source is constant voltage. So if those LED are the same type, then I don't need to worry, because also they will take what they need from the source. So I don't need to worry. So they should get the same illumination.
So
Depending on, of course, the manufacturer of that. Because in general, there are many types of LED. If you go to any store and you bought LED, you will see, for example, one LED that works at 800 illumination, while the other at 1,500. So that you will see, of course, if this one 800, 1,800, what's the difference is the internal resistor. So the differences between them, they are all sharing the same current. Why they give different illumination? Because the internal resistor or the manufacturer, this can give 1500 or 800. So you will see different illumination because of the material of the manufacturer. While if you have the same type, they should be the same, of course.
And I was more asking the difference between the series and parallel with that setup right there.
So here,
how do they compare the series, the two LEDs in series? How do those compare to those in parallel? In terms of the light output, so let's say the
okay, so if you are connected in series, they might not, like if they are different manufacturer, they might look different than in AC or in parallel. Because if they are not the same manufacturer, or this one is different, for example, this one 800, this one 1500, the illumination, then the equivalent circuits, they should share the same currents, not different currents like here. Then they should give different illumination depending on the circuit analysis that will be. So you need to calculate the currents, then there should be a relationship, an equivalent. I don't have it right now, but there should be some relationship how to calculate the illumination that can be found from the LED. So this can be like a little while ago.
Thank you.
Now I want to move to chapter 7.1, which is sensors and instrumentation. So when I say sensors or electrical sensors, what do I mean? Or what in general, before going to electrical sensors, what do I mean by sensors? Sensing.
Measuring something?
Measuring something, right. So anybody, like if we want to have a complete system, we must have an ability to measure something if I want to do any part. So the human body has 5 sensing. Now, if we want to go to the electrical system, we need to have something to sense if we want to make any control. For example, if I want to control the temperature, how the AC is working is the heat or the central heat is, for example, is working, and after that, at a certain temperature, it will be turned off. How can I know, or how can it reach it? When will it stop when it reaches a certain temperature? How can I read this certain temperature? Through a sensor. So this sensor is what's doing what? Converting the temperature to electrical energy, or to electrical system. So sensors in general converting physical simulation to electrical signals. Any physical. And also sensors are usually small, and there are some types of sensors that can be susceptible to noise. After doing the sensors, I measure the temperature. So now I want to say, is my temperature, if, for example, I set the temperature 72 degrees Fahrenheit. So after I measure this, my target is to reach, for example, 73. The actual 72, my target to reach 73. So I need to make a condition, which is compare between them. They let the AC run. And when it's reached the 73, I need the AC to stop. So I need something that determines the differences, which is we call it conditional. So what's coming, that's manipulating the desired from the processing, or the actual, or the recording. So I'm conditioning, comparing between the actual and the desired. So I have two things. After that, what it goes, it can go to amplify the signal or shift the signal to another range. I can do many things with that. But I need to know like how to do with this signal. It's not only sensing this, I need to do something else, which is like, as we call it, conditioning. Now I just want to go also for a quick some stuff. So sensors, some examples with sensors. We have things we call it LDR sensor. So LDR is called light dependent resistor. And basically this is what resistor changing its value depending on the lights. So based on that, I can convert the lights to electrical signal. So what's happening after that? I can do some action to them. So for example, if I have a street lighting, if there's sunlight, turn off all of these street lighting. If there is sunlight, turn on. So we can use LDR in street lighting, which is light dependent resistor. We can use this also in your smart home for the curtains. So you can for your window. So you can move the curtain so it can cover the sunlight when there's sun. When there is no sun, it can be turned. And there's another thing called thermal or thermostat. I'm not right sure about the spelling. Sorry about that. Thermostat. Which is temperature sensitive resistor. So this is doing what? Converting the temperature or to electrical signals. Or we can say this kind of things, which is the resistor that changes its value depending on the temperature. So this is also very used in applications to measure the temperature. And there are many applications with that. And we have also force sensing resistor. And we have speed meter. Speed meter also, I'm converting the speed to signal. So why we are using these sensors? Because we want to control the system. or the electrical system. Or we can say control the system, not only the. So in general, I need to have for any systems, I must have a desired value, and there should be a comparator between the actual value, and here this is a comparator or conditional or conditioning to get the error, which is desired minus actual. Then, after determining the error, I need to do some action. In order to do the action, I must have controller. So this controller will do an action to correct the error. So the controller will correct the error. The target is to let the error equal to 0, goes to 0. That's the controller. What's the controller do? Then I have the object that I need to be controlled. Object to be controlled. After that, I should have my targets, which is the actual. How can I measure the actual in order to do the conditioning? By using sensors. So this is the control system in general. So this is the fundamentals of that. But we see some words that we couldn't understand. Like object to be controlled, controller, sensors, desired, actual. Let's see example for that, which is in the cruise control for the car speed control. I have a car, which is the object to be controlled, which is the car speed, the object, or the car that I need to be controlled, car speed. Okay, this is the object to be controlled, and my target, or I measure the actual value of the speed. Okay, then how can I measure this? Using what? Speed meter. Is that right? This is the sensor, speed meter. So then this actual speed, I compare with the desired speed. So this circle means comparator. This negative, positive, which means desired minus actual. So I can say, for example, the actual I want at 70 miles per hour, and this, I mean, the desired I want it, the desired 70 miles per hour, and for example, the actual is 60 miles per hour. So I have a difference, which is here the error. Okay, so how, after that, the error, I need to have a controller. What's the controller for controlling the speed? The accelerator. So the accelerator will be, for example, since the error is 70 minus 60, which is 10, then the accelerator should be forced or to increase the speed, or should be turned on, then the speed of the car will be increased to get, for example, a new speed, which is 70 miles per hour, then 70 miles per hour will be measured, the error is 0, then the accelerator will stop, or will not run the accelerator because now I've reached the 70 miles per hour. Then if I go drive more, since I have friction losses, or sometimes the ground, it will not be a constant speed, so it can change depending on the road. So the accelerator will also see, or the conditioner will see what's happening, the difference between them. Is that clear? Another example, temperature control. So I have a reference temperature. Which is, for example, 70 Fahrenheit. And I have, for example, room temperature that I need to be controlled. The object needs to be controlled. So I measure the actual temperature. How can I measure it? Through a sensor which is called thermistor, for example. I'm measuring the temperature. So this is actual temperature. So I must have the error, I measure the error between the actual and the reference. Then if there is a difference, I will make the AC units should work and until reaching the desired temperature. Then after that the AC will be turned off. Is that clear? Any questions? So these informations are not mentioned in the notes, so you will not be tested on that, but I just want to mention this for you to understand how the control operation are working. Also, there is a course, separate course called Control System in Electrical Engineering, which talk about how can I control any system. And I think there is also another engineering, like I think in aerospace there are some control courses, and I think in mechanical engineering there are some control courses. So you might be familiar with this. Okay, now there is a concept called Wheatstone bridge. There is this circuit techniques has been built to measure the resistors. If I have unknown resistor or changing resistor, how can I measure this? Why I do need to use this? Because sometimes, let's go back to the applications, LDR, light dependent resistor, thermistor, temperature sensitive resistor, force sourcing resistor. So this kind of sensors are variable resistors. So in order to get the electrical signal for it, I need to convert this from resistor, or I need to find the value of this. How can I measure the resistor? Which is using Wheatstone bridge. So Wheatstone bridge is voltage source with 4 resistor circuits. And it's used to measure the Simpson resistors, like thermistor, photoresistor, strain gauge, etc. So this resistor that we need to measure from the sensors, we used to call it RS. So that we want to measure. And we have the other resistors that we should know, and they should be fixed, which is called RF. So we have one resistor unknown, and the other 3 resistors are known. So I need to put them. I can insert them, I can put them. I know this resistor is this, and this resistor is this, so we have the unknown resistor. So, and we prefer to choose these resistors, the other 3 resistors match each other. Or match, we call it the nominal resistance of the sensor. Then we calculate the output voltage. So if the output voltage, based on that, we can use this to determine how much the resistor is. If the output voltage is 0, then all of these resistors are matched. So Wheatstone bridge circuits, this is the equivalent circuit for that. We have this voltage DC, RF, and RX. This is that we need to find. This is the unknown. We have 2 approaches. We can call this RX, or we can call it RF plus RX. Okay? So I do want to go to the derivation, but there are 2 formulas for that. This one, the exact formula. This one, the approximate. So this one exact. This one, the approximate formula. So we don't want to go to the derivation. You are not required to know V and VB. What you are required to know the equivalent circuits, and to know V out and V out approximated and V out exact. And you can write them in your note sheets. So my target is to what? After finding, to know my targets, after knowing V out, or to find V out, if I know Rx, or if I know RF, I know VDC, I measured V out through the digital multimeter, so then I can find Rx. Let's see a quick example, then we can finish. So just these two formulas you need to know. So a Watson bridge with a strain gauge, and the strain gauge has the nominal resistance 120. So this is RF with a maximum delta R. Determine the maximum V out for the sensor and exact and approximated VDC equal to 10. So this is Watson bridge circuit. Then the first thing, write the formula for exact. V out equal to VDC times Rx over Rx plus Rf minus 1 half. And for the approximate, V out equal to VDC over 4 times delta R over Rf. How can I find them? For the exact, we can say we know Rx, Rf, we know delta R. So we can say Rx equal to Rf plus delta R, which is 120 plus 0.246, then 120.246. Then substitute this. We have VDC equal 10, Rx 120 over 120 plus 120.246 minus 1 half. Then the answer will be 5.12 times 10 to the 3 volts. Here, for the approximate, VDC 10 over 4 times delta R, which is 0.246 over RF 120. And the answer will be 5.125 times 10 to the 3 volts. So we see that the exact and the approximation almost the same with very small error. Here there's 5, here there's 5. So in this case, we can sometimes say it's worth to use the approximation because it's easier. I don't need to do any calculation. Just VDC over 4 times delta R over R. Any questions? Okay, so that's what's required from you to know about Watson bridge. The equivalent circuit, the formula for the exact, and the formula for the approximate. We'll see you in